So now discussing from prediction to action, a journey through the core mechanisms of modern AI. So the core task is how do machines learn from data, right? So the fundamental goal is to create a program F that can learn to map inputs X, right? Let me show you. Learn to map inputs X to outputs Y by observing examples. So a neural network is a powerful type of a program that is designed for this. It's a function f theta of x whose behavior is determined by a set of tunable parameters theta. We want to find the theta that best approximates the true underlying pattern in the data. So p theta of y given x, this is conditional probability, is equal to f theta of x. Right. Moving on. The simplest building block, the single layer network. So the most basic neural network is a single linear layer, also known as a perceptron. It computes a weighted sum of its inputs, y is equal to wx. This simple model is effective for basic regression or for classification problems, where the different categories can be separated by a single line, which is straight. Right. The limit of simplicity and the need for depth. So a single network has a fundamental limitation. It cannot solve problems that are not linearly separable. For example, it's impossible for a single line to correctly classify the simple equality function. Right. So how does a network actually learn? So learning is an iterative process to learning is an iterative process of adjusting the network's parameters theta to minimize error. This process is called a gradient descent, which follows a simple recipe based on the MLP, that is maximum likelihood principle. So we first need to define a goal, that is measure the network's error with the loss function L theta. The goal is to make this loss as small as possible. Then we need to find the direction. So we calculate the gradient, that is delta of L theta, which points in the direction of the steepest increase in loss. So this is delta L theta, and then we take a small step. So we update the parameter theta in the exact opposite direction of the gradient. So since we are taking exact opposite, we need to subtract it. So minus eta is basically this learning rate, and this is the gradient of the loss function. So we change the parameters in an iterative manner, right, for each step. A classic dilemma. So the problem of overfitting. So as a model trains, its performance on the training data consistently improves. However, its ability to generalize to new unseen validation data can start to degrade. This is called overfitting. So the model stops learning general parameters and general patterns and begins to memorize the noise and quirks of the training set. So basically, this is the problem of overfitting. The optimal stopping point is here, but when once it starts going ahead more than that, once it starts going for more iterations, the validation loss increases and the training loss basically keeps on decreasing. So this is the point where we need to stop. This is the optimal stopping point where the loss is minimal for the validation as well as the training loss together. Now a modern wrinkle. So the double descent phenomenon. So the classic U-shaped curve isn't the whole story. For very large, highly parameterized models, a surprising phenomenon can occur. After the initial overfitting peak, the validation loss can begin to decrease again as the model continues to grow in size. This double descent helps explain why massively overparameterized models like today's LLMs can generalize so effectively. Right. So the previous graph was up till this point, right? That it was decreasing and then there's a sudden increase. But when we overparameterize models and when we keep it running for more iterations, then there would be seen that the validation loss would start decreasing. So that is basically uh, what we can see in today's LLMs that can generalize effectively and reduce overfitting. So what about sequential data? So a simple approach is a Markov assumption. So the first attempt to simplify the problem is the Markov assumption, which assumes that each element in the sequence only depends on the one immediately preceding it. This is the basis of the bigram model. While simple, its memory is severely limited. Its memory is since its memory is severely limited, it cannot capture long range dependencies in the data. Its memory is severely limited. Now moving on. So remembering the past, the recurrent neural network. So an RNN solves the memory problem by introducing a hidden state h. At each step, the network takes in the new input xn and the hidden state from the previous step hn minus 1. It uses both to update its hidden state hn and make a prediction. This loop allows information to persist and travel through the entire sequence. Now the modern powerhouse, the transformer architecture. So while RNNs process sequences step by step, the transformer architecture can process all elements in parallel, which allows it to capture complex relationships between any 2 points in this sequence, regardless of the distance. So this power comes at a cost. Its computational complexity grows quadratically with the sequence length O of n square compared to the linear complexity of an RNN, which is O of n. So the architecture that powers today's LLMs is basically this. You can see RNN basically has O of n complexity, while transformer has O of n square, and parameter versus length n basically both are independent of it. Now a new paradigm from prediction to action. So far, our models have been passive observers, learning to predict from static data sets. But what if the goal is not just to predict, but to act also? So how can a system learn to make a sequence of decisions in an environment to achieve a goal? This is the domain of RL, which is reinforcement learning, right? So we have agents that are basically the learners or decision makers. The environment is basically the world the agent interacts with or the surroundings. Now, we have basically this as our mechanism that works for reinforcement learning. So firstly, the agent observes the state of the environment, right? Then it chooses an action based on its policy, right? So it chooses an action based on its policy. Then the environment transitions to a new state and provides a reward, right? So the goal is the agent's objective to is to learn a policy that maximizes its total cumulative reward over time. Okay. Now moving on, learning from trial and error, the reinforce algorithm. So the agent's policy is a neural network that maps states to actions. To improve it, we use gradient ascent to maximize the reward. For a given trajectory of actions, the update is guided by two questions. Which direction in parameter space makes our chosen actions more likely? And how good was the final outcome, that is the total reward of this trajectory? So how to make this trajectory more likely is basically given by this term, delta theta of log theta p theta tau. And r tau is basically, was this is answering the question, was this trajectory good, right? Now, the full spectrum from prediction to autonomous action. So, our journey has taken us through three fundamental paradigms of modern AI. First is prediction using deep learning, the core engine for recognizing patterns in data. Then we have the sequence, that is the modeling, RNNs and transformers, right? So, extending the prediction to understand the context, the order, and long range dependencies. And then we have moving on to action, which is reinforcement learning, using predictive models to learn how to make optimal decisions in an environment. Now, these components are not isolated. State of the art systems like AlphaGo combine deep learning and intelligent search and RL to achieve superhuman performance.